Hello everyone. My name is Elias, and I'm gonna be talking a bit about an interesting story in Starcraft, a very old game that had a buffer overflow, and hackers used it to modify the game. And then we fixed the bug, but the community was upset, so we had to emulate the bug, so they're happy again, and they can play the maps they designed based on the buffer overflow. So just to mention real quick that Blizzard Entertainment does not endorse reverse engineering at all, but we did this exercise to understand how they hacked the game and whatnot, and how we can emulate it. Real quick, so I'm an anti-cheat engineer. I have been working 1 year in Blizzard. I'm also a technical writer, and I have interest in emulators and low-level programming. Also, I'd like to thank lots of people, my colleagues, the community, and tool makers. So a bit backstory. So Starcraft is a real-time strategy game. It was first released in 1998, so this is really old now. And then we released an expansion pack. What's important here to note is we all right, so I'm basically emulating the latest patch that we had for 8 years, 1.16.1. So from 2009 until basically the first modern patch in 2017, we gave enough time for the community to fix the bugs on their own, to do those maps, to exploit the game in a positive way. And so that was the first patch, 1.18, and then we remastered the game, and then the community was expecting that their old maps work, although the buffer overflow is long gone and whatnot. So the goal is the latest versions from like 1.21 and up, they should support maps created for 1.16.1 without modification, because the authors maybe are now 40 years old, or maybe they lost interest in the map. They don't even remember how they modified the map and created the mods and whatnot. So the game, since it was written like a really old time, it had lots of bugs and buffer overflows. And one buffer overflow was in something in the triggers mechanism in the game, which is like a logic that you can have inside the map, and you can have a very minimal programming language where you can set certain conditions in the map, so you can modify the scenario, how the game plays and whatnot, move units around and create units and do some conditions. So the exploit was in the code pass that handles extended unit death trigger, which is basically a counter. When certain unit types die, there's a counter. You can read that counter and you can write to that counter. And so that counter is an array, and it had a buffer overflow in that array, so you can do read or write anywhere. So we did not want to release patch 117 because we would break the games. So we skipped all the way to 118, and we decided that's it. We should really kill the bug and move forward. So the maps, basically, they were the EUD-based maps were thriving in South Korea. So I don't know any Korean, and most of my contacts were with Korean people. And so I had to use lots of translation to help me communicate with them. And the EUD triggers live inside the map file. So essentially, if I wrote a map, I give it to you, you're running an exploitable map, and you have to trust me whether I'm giving you a malicious map or a legitimate non-malicious map. Luckily, they loved the game so much, they weren't distributing viruses or any remote code executions through the maps. So, but they did interesting stuff. They wrote games like Random Tower Defense. They wrote Mario inside the game. So let me show you real quick the game for those who haven't seen it before. And sorry. So here we have a professional player playing the game. And basically the game, you have units. You command the units, you play against other enemies, and you have buildings. So there's a map editor program where you can design the playing field, initial unit position, forces, neutral units that do not attack anybody, and so on. So this is the game, how it looks like. And what I'm going to show you is going to be like, it's the same game, but they hacked it so much that you will not recognize it. So a simple example, let's show you, like, they made a bouncing ball game. And so in this map, basically the game is not playable by the keyboard, but they could even manage to read the internal keys table, keystrokes from the memory of the game. And so you can play this bouncing game or network with your friends using the keyboard. So this is already way beyond the game capabilities. All you have to do is simply run that map, which contains a bunch of read and write memory instructions, and they achieve this effect. So this is the same game after emulation. Now, I don't support graphical emulation, but I support all the other things. So, for example, instead of seeing the ball, we see one unit repurposed here with a custom sprite. And here I don't support custom sprites, but we can see what they used originally to make it bounce and whatnot. Now, this is not so impressive, I would say, but this is more impressive. So what we see here in this map, actually, they change all the graphics, they add keyboard support, they even hide the console of the game, and it's multiplayer, so like they're collaborating to fetch the key and open the door and whatnot. What is even interesting in this, I'm gonna show you real quick just how far they went, the Korean map makers. They created a language on top of the buffer overflow, and then they created a level editor for Mario. And it has like 20 levels, and you can create your own levels, drag and drop, and then play it within Starcraft. So that's pretty impressive, and it was pretty difficult for me to understand the whole thing that they have been building over many years, and with the language barrier. So like this is an example, they have their own physics engine and whatnot, and all within the game, but you can still see that well, the primitives, essentially, everything probably looks like high level, like round, dot set, screen set, whatnot, but eventually they're touching lots of memory location in the game, and finally it boils down to set memory or read memory. These are the primitives that drive the whole modification of the game. So my goal is to emulate those maps, which basically can do a read anywhere and write anywhere, without basically modifying the game, the map itself, because we can't anyway. And of course, they devised copy protection for the maps, where it's hard for us to reverse the map. It's hard to. They want to protect their own intellectual properties from other map makers. So, like, that's my map. You cannot redistribute it. So I had to deal with that as well. So yeah, this is the most impressive map, I tell you. And there is another map which I started with, and luckily that was the most popular map. And once I supported it, most maps worked. So let's talk a bit about the map file format real quick. So the map file format is a MPQ archive. It's a common archive used in most Blizzard games like World of Warcraft or Warcraft and whatnot. And inside the MPQ archive, there are, like, it's a file system like zip files, and it contains one particular file called scenario.chk, and chk stands for chunk. And basically chunks, and here I'm showing you just a third-party chunk editor where you can open the map and see the chunk file. So the chunk file is a simple, has a file format, very simple. It contains 4 bytes chunk ID and the chunk size, and then the file has an array of chunks. Every chunk, here we can see like there are multiple chunks. Different chunks have an associated handler that parses, knows how to parse that chunk. And in particular to this talk, we look at the strings table chunk and the triggers which contain the logic. So the logic, if it refers to strings, then the strings are to be fetched from another chunk. And there are other things like initial unit placement and terrain setup and whatnot. The string table is, some chunks have the subheaders within the chunk headers. So like the string table, for example, contains how many strings are there, where are the offsets, and then after that header, there are the actual strings pointed by the offset with the base of the chunk start. And the code simply read the whole chunk, so it doesn't really do the actual string table size, it counts on the chunk size. And that means they can have less strings than the chunk, and so they leverage this to add more logic, because the trigger section has a limit, so they expanded the limit by using caves inside the map file. But the game doesn't even read the other chunk or the strings table to read more stuff, but this is how they, I will show you how they transition from the triggers chunk to the strings chunk to get more execution and more complicated logic. So like this is, for example, this is the 4 bytes str, the 4 bytes array, followed by the size of the chunk, offsets, then the strings. Then when the actual string table finishes, we can see here is the limit of the last string table. And the rest, what we can see within the strings table is more triggers. But the game normally do not read triggers from this location. But there's a bootstrapping code and trigger compilers are created for the language where they can redirect the trigger engine to read more stuff from memory from another location. So triggers essentially contain 2 things, conditions, and if the conditions are met, they are executed. So we have conditions like after a certain time, for example, then do an action, or if a player moves the unit to a certain map location, do something else. And in particular, we have the EUD, the extended unit deaths, which are counters that you can use. For example, if I lost 5 units of this type, do something else. You can play wave files, display text messages, spawn more unit, give resources, and whatnot. So this is the structure of a trigger. So the trigger is an array of conditions and actions. And the condition structure contains this condition, what player it involves. So run it only for player 1, player 2, or current player. And also a condition contains opcode, just because there are so many conditions. But we're interested in one condition that has the overflow. I'll show you the code path leading to it. So like this is the conditions table. There are lots of conditions. And this is the condition in particular that counts the unit deaths. And the action, there is also, you can modify the count of a certain unit deaths. So the code simply, once the triggers are read from disk, they are parsed. The condition code, it runs through all the conditions. If all the conditions return true, it executes the action part of the trigger. So triggers are like essentially if, the condition, and then the body, the actions. And here we can see the trigger condition, very, very simple. And then the execution, basically. Now, for map makers, they can use visual editors to edit the map and edit the trigger sections. There is a visual editor, basically one can use visually construct the condition. Or they can also see the condition in a textual format, like it shows condition and then the actions. And it's very blurry here, but there are big indexes here that the game does not validate, and those indexes, based on the array that they overflow from, they resolve to absolute addresses after we do the overflow calculation. I'm gonna show you more in more slides. So the game does not validate the trigger parameters, so it simply reads it from disk, adds them to a linked list, and executes them. So if the player index is out of bounds, it's exploit. So here we can see in the arrays, we have an array here using two user-controlled indexes, W type and DW player. And in the assembly, we can see here, basically, this is the read condition, desk count, it returns the value. And this is user-controlled, so eventually they can, in the script, they can read anywhere they want once they control the ECX, which is a player index in the trigger structure. And also, we have the set condition. The set trigger action lets you put a value, increment the value, or decrement the value. So the write is you have to write a constant, but either it's plus equal, you are adding to a memory location, or a constant, or subtracting, or setting. There is no primitive such as memory 1 equal memory 2. You cannot copy two values. You don't have this primitive, so, but it's very important primitive. And here we can see the write primitive. This is the code as well. It's actually setting the condition and also using two attacker-controlled indices. And this is the assembly code, and this basically you can use it to write anywhere you want. This is the premise. Here, this is another example showing how the triggers look like in text form. And basically, if those indexes, they are displayed here in text form, but if they are beyond the range, they'll be big numbers. And eventually, everything resolves to absolute addresses. So now comes the problem. If I have a malformed map, how can that reads or writes anywhere? Is there a way to emulate that buffer overflow to give the same behavior in a new game? So we fix the buffer overflow, the memory layout is different, internal game structures are different. Maybe we don't use regular arrays, we use vectors and bounded arrays. We don't use linked lists, we use standard lists, and so the links are hidden from us. They are private members of the standard library and whatnot. So there are so many challenges to give the impression for the maps that they are really dealing with old data structures. And again, they were the maps they did had indexes hard-coded for version 1.16.1. That means it's only on Windows, and it's only for this version of the game, the old version of the game. So can we really deal with all those challenges, like new game, some addresses are gone or different formats, and also can we write the emulator so it works on any operating system, which is something they didn't have. They had to develop different maps for different versions and different platforms. So I had to tackle those problems, and I came up with a three-step solution. Basically, get all the maps and try to see what are the addresses used by the maps. And if I can get that, I have to build a table somehow and link those addresses to variables in the game. So this whole research is data-driven. I need to understand what are the global variables in the game. After I identify everything, I had to intercept and emulate. Any out-of-bound index, I had to emulate and then do the translation from an old address to the new address in the game. And this is the interception part. The emulation part, basically, if there are memory addresses that existed in the old game, they don't have equivalent in the new games, they have to be handled by code. If there were pointer manipulation, if you add a pointer in the old address space, you add a constant to it, it leads to another function in the old address space. That pointer arithmetic is nonsense for the new game because maybe you need to add another constant to get the same function that you wanted to arrive by doing pointer arithmetics. So I cannot just do a pass-through translation where, so that's the old address and that's the new address. Let's just do that, rebase it and let them write. So I have to filter out some dangerous read-writes and do some adaptation, transformation of the data if needed from old format to new format. But I had so many challenges to that. The first thing is, it's an old game. I didn't have sources. I had sources, but didn't have the exact source snapshot from 1990, 2009, and no PDBs, no nothing. And also I had to understand what is the intent when they write to a certain memory location. Sometimes they write to the memory location, but it can mean so many things. And the interception, once I identify what they're doing, I can plug in the emulator at the overflow case. And the last step is basically to emulate the intent of the access. So the reverse engineering challenge, I spent 3 weeks trying to reverse the game just enough to be able to start to identify global variables. So I started from scratch. I took the binary from the public, from the internet, and I found the closest source code snapshot. It's not exactly 116, but it was very close. And then I started trying compilers. I didn't have the original programmer. He wasn't around. He left the company, and I didn't know what exact compiler version, what compiler switches, optimizations, and whatnot. I had to try very different versions of Visual Studio until I found Visual Studio 2003, which gave me a very, very close binary to 116. So I used patchdiff and diaphora to do just some diffing to help me identify the functions in the public game version. But of course, it was very, very limited. I couldn't really get the optimization switches proper, so there are inline functions. The old version of the game was very, very optimized, very weird calling conventions. There's no consistency whatsoever. Global variables, the diffing tools that I used, they don't identify global variables. So I had to, and that's my goal, to get the global variables. So from the function name, I could scan the sources and see, okay, so this is the global variable that they were using. And I rebuilt the global variables, I identified them. Anytime I find like a limitation, I had to manually reverse engineer the game by looking at the source code. And I also used lots of scripting, lots of it, to rebuild the data structures. We had like variable size structures and whatnot, and I needed to redefine them in the database of IDA, so they look exactly like the sources, so I can do proper emulation and understanding of the intent of the memory write. So I put the source code on one side and IDA on the other side, and I did my best to make the disassembly look very clean, so if they ever ask for any address in the game, I know exactly what they want. So I spent 3 weeks just putting source code on one side, disassembly on one side. I worked a lot with the decompiler as well, and it's very accurate. So this is decompiled, this is the source, and they're almost the same. Lots of scripts. I have around 50 scripts, snippets, and lots of on-disk scripts that I wrote to rebuild tables in the database from elements from the sources. I would paste some code snippets, like some maybe names and whatnot, and write a script to batch rename and batch create structures and so on, so that the database is fully documented. And then, after I did that, the remastered game, 118, collects collects telemetry. And so I went to our server, and I downloaded 600,000 maps. And then I wrote a tool to scan the maps, scan the triggers, and see if there are out-of-bound indices in it, and classify them as those are the maps that require emulation. And I ended up with 18,000 maps that I processed and extracted unique addresses from and built a table. So here, for example, is a snapshot of the output of the tool saying like this particular map, we're accessing 2,300 addresses, of which 276 were unique, for example. So I was dealing with lots of addresses, and it's overwhelming the amount of variables they needed in the game. So once I processed the map, I generated a text file containing all the addresses. I wrote an IDA Python script to take an address and aggregate them. If the addresses are consecutive and they happen to belong to an array, I emit a table saying, well, you know, this address has this size, and this is the variable name in the game, in the sources. And so I built a table of almost 800 entries based on the scanning the 17,000 maps and generating that table. And that will serve as a translation table between all the address, their size, and the game variables. So now I have like really symbolic names for addresses, for which if I want to use my C++ emulator, it can, once it computes the absolute address, it knows the variable symbolic name, and it can do the translation between them. But static address discovery was not enough. So the initial table contained those from the maps I scanned statically. But when you run the game, the map have a bootstrap code because some maps were created by the compiler, like the Mario and whatnot. And there are dynamic triggers. So in the trigger language, there are no loops, no function calls, none of that. So they wrote a scripting language and a compiler, and they make self-modifying triggers that can link to make loop constructs and dereference memory. So I needed a way to dynamically understand what happens beyond the bootstrap code, beyond the static memory accesses. So for that, I needed tools to, if suddenly during runtimes there's a weird address that I don't know where it came from, I need a way to be able to emit a pseudocode that let me see how things happen in the game. So I developed a tracer that gets injected in the old game, intercepts all out-of-bound indices during the whole game play lifetime. And every time I hit the address, I try to identify it. If it's not in the table, I reverse engineer enough until I understand what's that address and where it came from. So here is just a simple slide showing that the hooks are set inside the old game, and I call the tracer, and the tracer will go look at the table and see if this is a known address. If not, it suspends the game, and then I continue reverse engineering and rename the address, add it to the Python table, run the game again until I can play a complete map and knowing everything that has been accessed. Nothing should be unknown. And so from the Python table, I generate a C++ table, and then when the old game is accessing something, I can look up in the table, and if it's not in the table, I know I should add it to the table. And so it's important to account for every address. Otherwise, the logic of the game will be incorrect. So also in the tracer, apart from the static table that we have from this here, there are some of them are pointers. So I had to instruct the tracer to dereference the pointer after the game start and build dynamic entries so I can follow dereference pointers. And this slide here, I show as well, I initialize dynamic items and add them to the lookup table of my tracer, like linked list of triggers, which are dynamic, controls, which are dynamic, graphical items, sprites lists, and whatnot. And I added into my tracer an ability to suspend execution when a certain address has been accessed and whatnot. And also, I wanted to like, if I have an address, I want to see it in a very, very nice way, like a program, from a programmer's point of view. So I need to convert read-write primitives to pseudocode, better than like condition and action and whatnot, like C code, so that I can see it as a small program and understand what happens. So to give you an example, here we have like a very simple case. If I have an address like this one, 518.7E8, and if we say plus 0C times 3 plus 4, it's accessing a cards array, second element, the P button pointer, for example. So I needed a way to really, if given this address, to tell me that this is the expressions they needed. And once I see that, I understand, oh, okay, they're trying to change pointer to the buttons, for example, and whatnot. I took it a step further to understand more, so I wrote a function using the decompiler and some metadata from the sources, such way that if I ask it for an address, it can display the address. If it's in a multi-dimensional array, it can show me the array base. If it backs by enum, it shows me the enum name and so on. If another address doesn't have enum, like it will show me in numeric indexes, for example. So with this level of detail, I can generate pseudocode as the game runs. This is an example of how the triggers look like. This is how it is, but it's not helpful. It's not like C code. It's not readable, I would say. So I wrote a transformation tool that will, so I defined my own language where I defined what is a statement, what is a trigger, and then I created something that converts from a trigger language from this format to C format. And then the end result will be like trigger function, if condition, and we can see pretty clearly what they are really doing, what variable, what is the index, what they're checking, and so on and so on. So now I have like a C program telling me, they're accessing this table at this index, they're adding this value, and so on and so on. So now I have nice source code representation. So let's continue real quick. And then I used conditional breakpoints as well in IDA to generate the code on the fly. So I put conditional breakpoints on strategic locations before the trigger is executed, before the condition, after the condition, and whatnot. And so this is just a screenshot of the conditional breakpoint that is executed within IDA. And this is how it's building the abstract syntax tree and emitting it as the game executes. So in this slide here, I put my tracer in like single stepping mode where I had to resume every time a trigger is executed. And every time I resume, I can see more of the code unfolding in front of me. So at any time in the map, I can suspend, enable tracing, and I can see what they're doing. I can also configure the tracer to be automatic, keep emitting the code as it happens. And so I changed the single stepping and I let it run. And as the map is doing things, I can see the code being emitted. That will help me understand what they're doing, what they're touching. So now we finished with the first step, basically, identification. Now I need to intercept and start the emulation. So what I did here, I show you the original code where we had an overflow. Now I check if it's an EUD map. Do not return 0. Instead, call the emulator. And in the other condition, the write primitive, if it's an overflow, call my emulator as well. Otherwise, just write to the original array. So instead of checking for out of bounds and returning early, I pass it to the emulator, which converts the indices to absolute address, uses the table, the lookup table, translates it to the new addressing. And so the formula is simple, really. Given the overflow base, I can compute the full address. And so I can inside my read emulation, for example, I compute from a player index and a unit type, I compute the full address, and then I pass it to the emulator and I say, hey, return at this full address in the old memory space, read that value and give it back to the map. And same, the write primitive gets translated to write virtual memory within the emulator itself. This is the address they intended based on the two indices that they passed. And so the whole emulation is really emulate, read, and write. So let's see how I did that. I had to extend the unit, the Python table, not just to have the variable names. I also now augmented them with, I grouped them under which source code file those variables exist. Like this, I can generate the backing table where from a variable address to like a symbolic, like at variable name, and this is the old variable address. So I'll show you how the code will look like. I run the generator script. It patches all the source files and emits an export layer that will export all the needed variables into another table. And so this is how it looks like when I run the inject the export code. Basically, it goes, because those variables are, some of them are static within the source file, but I need to access them from the emulator. So instead of changing all variables to make them global and whatnot, I append to the end of the source file real quick the EUD pointer equals and then the address of the variables. And so like this, I have now the new address. Every time we compile the game, this will resolve to another address, and this has the equivalent old address in the table. And if we introduce any incompatibilities by increasing the new array size versus the old array size, the generator will assert. So I know that this needs extra attention if in the future they change the structures in the game. And after I have exported all of those, this is here an example real quick. Sometimes, as I said, we have static variables. And if I export them as is, I will have collision between other static variables and other source files which have the same names. So the generator can let me override the name and prefix it. So like in the source file, it's called freehead. But there are other freehead variable names in other source files. So we can tell the generator to change the name. So they are unique exported variables. And then this is the final lookup table containing the old address and the actual in-game address, the real address. And there are some things, like they needed temporary storage. They use alignment gaps to store variables in the game and whatnot. So they are nothing. I emit them automatically. They don't have any backing data in the real game. But I provide them scratch space for them dynamically. Now here we notice there are some null pointers. They do not have backing data at all inside the game. So in that case, this means the structure has changed completely. I cannot do one-to-one translation anymore. So I had to write an adapter. And so the table now also now contains a flag. That flag tells what adapter, so I have like a base class, and then I have a bunch of subclasses that know how to deal with certain emulation types. And I have a factory class that, given a flag, it knows how to create the appropriate handler for a given address. And in this case, like when this address is being accessed, the emulator knows it should create a handler of this type, and that handler knows how to do the read virtual memory or write virtual memory. And there are a bunch of adapters I wrote for multiple non-basic types. And this is a quick overview of the emulator architecture. Essentially, this is the old game, and this is the new game memory. And so the emulator itself contains a shadow table and virtual memory to handlers mapping. And so in the table here, the emulator can refer whenever it needs an address. It goes to the table that I showed you, and it has the old address, its size, and the backing data, and some flags. And then also, if it's not in the table, it needs code. then adapters will handle the request. So from the emulator, it can either go to the table itself or an adapter, and there are multiple adapters, an adapter for one structure or the other and the other. And the emulator, basically, if it needs a question, it will eventually, after it does what it needs to talk back to the game and get the results. There are two restrictions. By the nature of this overflow, they can read 4 bytes only, and they should be aligned. And the values they read 32 bits. So if they want to read a single byte sometime, or in the middle of the array, they have to issue read before a bit, read 4 bytes before, read 4 bytes after, and take the last 2 from the first one, the first 2 from the second one. And so they had to stitch values together because they cannot read at odd addresses. So the shadow table contains some the real contents of the old game, in case I want to do some emulation of pointer arithmetics. If a pointer in the old game needs to be translated to a pointer in the new game, I do the computation in the old game, and then using the shadow table, I can tell what was at the original game memory. So I do not have a copy of the old game memory completely. I have maybe like 8 kilobytes of the needed data of the old game within the new game, just enough to support pointer arithmetics. So, and then I have specialized adapters, as I said. Basically, addresses no longer exist in the map, non-standard data types, bounded data types where I don't want them to write to an array a value bigger than a certain index. That has to be handled by code, not by pass-through emulation. And the gist of an adapter is just basically an adapter, if it's subclassed from the basic one, they have to implement read virtual memory, write, backup. It's important to restore all the changes the map does, otherwise it will leave the game state inappropriate. So an adapter should, at initialization time, the emulator will call every adapter and ask it if the adapter needs to back up the code, and it knows how to back up based on the data it's emulating. And when the emulator deinitializes, it calls every adapter to ask it to restore the memory. And I had to add something called deferred write, where they do changes incrementally, and I don't want to do the side effects as they write, because maybe they're copying a new sprite to the game, and I will wait until they write the whole sprite, then I will convert the sprite from one format to the other. So deferred write takes place after a whole trigger is executed. I buffer the writes, and I get the summary of all the writes as a big buffer, so that speeds up the emulation. So the basic idea of an emulator is really simple. Given an address, I find it in the table. If I don't find it, I assert, I tell them this map is not supported. Otherwise, once I found the item, which is an adapter that is responsible for handling that memory address, I ask the adapter itself to read. And similarly, this is inside the adapter. This is the simplest adapter, which basically takes the backing data and the offset. The backing data is the new variable in the game that we got from the table that the generator created. And I simply read the value by adding the offset. So I change the base from the old base to the new base and return it. That's the simplest adapter. So in this example, in 1.16.1, at a certain address, we had that variable, but at current compilation, like one of the compilation of a new build, it happens at another address. But it doesn't matter, as long as I have the correct backing data base address and the offset, I can have the same effect by reading from the same array, but they're simply relocated. And here I'm showing you real quick, sometimes the emulator knows how to cross boundaries from two independent elements. Like one handler can be reading one part of a word, the other will be reading the other part from another adapter. The emulator will combine the values and give you the uniform value, but from two different sources. And the sources could be One is a direct translation just from a regular array. The other could be backed by code. So the code really did the computation and read the value, and it's served. So the adapter knows how to cross boundaries between elements that are adjacent. Now let's talk real quick about the primitive that was missing. Basically, the memory assigned, like dereference a memory and assign to it. This is what we had. We had write to a memory, a constant. The assignment operator is plus equal, equal, minus equal. And we have the read primitive, which is if comparison operator constant, then do an action. This is what we have. But how can they do memory 1 equals memory 2, given only those two primitives? It's saying if an action can be just assignment. So it's very important for them to really dereference and copy from another memory location. So using those two primitives, they managed to create a third primitive. Anyone has an idea? Yes. All right. So basically, they use a very genuine trick. Basically, they use binary search, and they split to have that primitive. They have to issue a series up to 32-bit 32 comparisons to copy a full value. By first starting, for example, in this example, is the value that they want to assign to greater than 8,000? If it is, then let's add that number, and so on. Then they subtract it, and they keep on divide and conquer until they have a copy of what they want. Then they have to restore the value they changed. So then they redo the whole thing to copy the var copy again back to the source. So they redo the same. So in worst case scenarios, every time they want to do an assignment, memory dereference assigns, they can emit up to 64 triggers, which is a very slow operation, but they do that all the time to achieve like high level of complexity. So this is really one of the most expensive. They don't do it often, but they do it a few times to link more triggers, and I'll explain what exactly. Let's talk about one adapter in particular, which is pointer manipulation. So pointers in the old game, of course, we cannot just say if they were writing to a pointer in the old game, we can just simply let them write it in the new game. We have to do pointer validation before converting from virtual address to what I call real address in the new game. So sometimes, as I explained in the memory assignment primitive, they spoil a real pointer until they get the value before they restore it. So if they're doing that sort of assignment, they're going to be destroying a pointer. And I cannot just let them do that in the real game. So I employ shadow values during intermediate changes. So basically, if this is the real memory, this is a pointer in the new game, this is a pointer in the old game, and they are doing that primitive to assign. They're gonna slowly decrement this one, and then re-increment it so that they got the value. I don't want them to be, I don't do the translation to real memory yet. So instead, I employ two backing variables, the shadow. So whenever they change in the emulator, I queue it in the shadow. I let them change uint32, which is the same size as the 32 bits game. And I have a dirty flag associated with it as well. So if that is not dirty, I can do the translation back and forth nicely from a virtual pointer to a real pointer. If it's dirty, it should not be done immediately. No changes should be executed unless the pointer is complete, meaning this one has a proper equivalent in the new game. And so I had this a lot, so I had to devise like a factor in the code, and I made a quick class for it where it implements the read virtual memory and the write virtual memory in that pointer adapter. Essentially, all it's doing is using the shadow table, the shadow value when needed, and And when it's done, I really now update. So when I can get a real, from the shadow pointer, when I can get the proper pointer that is in the new game, if that function returns null, then it's not complete yet. If it's not null, it means I found a real pointer. Then I really touch the game's pointer with whatever they wanted to change. And then I mark that as non-dirty. Some buffering. This is another example of function pointer manipulation. They change function pointers in the game. For example, they access an array, they access the P button function pointer to action button. They add to that function pointer a constant, C0. Now in the old game, if I fire up IDA and I go to that address, add to it C0, it really resolves to a proper new function. So I had to also be able to know what does it mean when I add to an old address another constant. What does it give me? Does it give me another function pointer? And then if it does, is it a compatible function pointer with this function in that structure? So in my table, I had to have additional information associated with the index saying what is the prototype. So it's a function pointer, and that's the prototype. And then when I do the translation, I can tell if it's a compatible pointer or not. So the basic idea is if I have a virtual address and we add to it a virtual offset, then the physical address is try to find a real pointer in the table for that virtual address with the prototype ID in question. If I find it, then I can really update the real function pointer with the real physical pointer. So that was also, I had crashes initially because I was passing through the whole structure. So I had structures like this, an array of such a structure. It's true that it contains regular types like integers, which I can pass through. But in the middle of the structure, I had some pointers, which those pointers need code handling. Those can be passed through immediately because they're basic types. There's no virtual or physical translation. So I had, this is another adapter that deals with incompatible arrays or structures. A structure in the old game looking like this layout, and the new game, it's another layout. And again, that structure also contains some pointers and shuffled members and whatnot. And I have to do the back and forth simulation between old format and new format. So basically, the read operation translates from the physical game to the real game, and the write does the other way around. So this is implemented in the read virtual memory adapter using a switch case. If they're reading from this offset, you do the translation like this. And so on. If it's not within those, then use the pass-through we call the base class to handle it. So we have big structures that I had to like really do the switch case on certain pointers and bounded variables within it, and to do careful translation between the two. The one big thing is linked list. In the old game, we were using handwritten linked list. And in the new game, we decided to use standard like STL's is equivalent, but internal. We call it BLZ list. So the triggers are no longer stored inside the linked list. It's like, it is a linked list what we store today, but it's another format, I would say. We don't have access to the internal previous pointers and next pointer, but the maps touch the next and previous to link more triggers and achieve loops and repetitions and whatnot. So I had to simulate linked list as well. And before I go into that real quick, I also mentioned earlier that they developed a script. They call it EP script, which you write in like JavaScript language. It gets compiled into the primitives, read-write primitives, essentially. And since you can write a very, very big script, you need to be able to do dynamic triggers. You need to introduce triggers to the game during runtime and based on conditions and so on. So they need to patch previous links, next links, and link more triggers to each other. So I had to, this is the old trigger structure real quick, where we have a trigger linked trigger node contains previous links and next links. And then what is important to me is the conditions and actions. So in the old game, every trigger contained a previous link and the next link. In the new game, those links are hidden from me by the standard template library. So the map makers assume that a trigger node contains 2 extra pointers for the previous and link and previous and next, and they patch it to link more stuff. So the adapter that handles that, these are the regular triggers in the current game. They are finite. In the old game, the triggers read from disk are finite, but then when those overflow triggers execute, they go to the last trigger and they link it to the cave area inside the string table where they have unlimited more triggers here, and they link it using the next pointer. What is interesting here in the emulation layer, I have shadow previous and next pointers. These are no longer existing in the new game, so only part of the trigger structure is implemented using shadow variables. So I do not use more extra memory. In this case, I reuse the same trigger data, but I introduce just 2 more fields for the missing fields in the new game using the shadow. And let them link and so on. So here's just a quick implementation of how I let them change triggers, and the game will pick them up nicely because the emulator knows how to iterate in that. I wrote a linked list emulator adapter where you can use regular C++ iterators to move within the virtual environment. So the game code is not really changed much. The emulator is really it's not intrusive. I can run my generator script and remove all the emulation code from the sources and clean things up if we decide to stop supporting. I don't have to change the game a lot anymore. Partial buffers adapter, real quick, is simply we may have a bigger data in the old game and smaller data in the new game. And this adapter will not fail if you ask it to read unmapped, non-existent data. It will simply return 0 without failing the emulation. Deferred write let me reconstruct data at the end. This is as well helpful for when they are transferring sprites and whatnot, when they are doing big memory transfers. I wait until they're done. When they're done, the emulator will call the deferred writes. Let's see, what is the last one? Bounded elements array. Sometimes we have basic types, which I can pass through, but sometimes I don't want them to write beyond the bounds within an array. So I have a small adapter that basically intercepts the read or the write, and it splits the value based on the array size, the base array size. If, for example, if it's a single byte, and they can only write 4 bytes at a time, I split the 4 bytes and check them if they are bigger than the adapters is max value and whatnot. And if it's big, then I put that in the shadow table only until it's within the bounds, then I reflect it into the game. So we have a bunch of adapters to handle sprites manipulations, unit manipulations, to access keys, the keyboard, MPQ adapter, this is the copy protection of the maps where they encrypt the triggers using an encryption key and whatnot. I simulate that as well, so encrypted maps will work, and they will only decrypt during runtime, so you cannot use any static tools to modify them without corrupting them. So different adapters really do things. For example, there's no legitimate way to read messages, chat messages in the game. And the map makers access the chat buffer in the game, and then they made a map where you type in the chatting window, create a unit, and then suddenly there's a unit on the screen. They call it chatting war. So the faster you type, the more advantage you have in the game. And I had to emulate that in such a way that when they read, I can give them, if they wanted to read the chat memory, which is completely different mechanism, I have an adapter that knows how to query the game to answer those questions. The storm list, pointers, structures with pointers, where it's partially pass-through, partially needs some computation and whatnot. I went very quick on this because I just went through 94 slides, so sorry if I was too fast. I can take a couple questions if you have.
Anybody have any questions? Hands? No?
Yeah, I have two questions. I was wondering, when did Blizzard realize the existence of EUD maps? Was it shortly after 1.16 or just when they started working on remastered? And my other question is, recent OS updates of Windows introduce features like ASLR and DEP, and did those interfere with EUD maps even on 1.16, like depending on the system configuration?
So they were. We knew about ED maps a long time ago because there were third-party launchers, basically, that modify the game and re-enable the buffer overflow, so that 1.16 already fixed the bug, but they wrote an external tool that repatches the game to remove the out-of-bounds checks. And so there were lots of third-party launchers, and not only that. Now, I showed you data transformation and data writes. They had launchers that were changing the protection of the text section and patching the code to fix some bugs. Now, I did not show you in the slides, but they are also, in some maps, they're trying to write to text section to change the behavior. So I had to emulate that by, so they were patching the code here. This is what they wanted. So instead of patching the code, I put some flags in the game to simulate the code fixes they were doing and whatnot. So DEP did not affect, but we had an old library where every memory allocation was executable. So even for data allocation, they were leveraging that to, I got a map, one shared it with a malicious map where all the heap allocations had the execute bit, for example. And those will not work even with emulation.
So does this also allow for the usage of BW API? Is it pretty instrumental for that as well?
Not really. BWI is way involved. It goes into more, it reads more stuff in the game. It has lots of, it injects a lot. It's a very big system. So BWI API needs more, we need to program it properly. We cannot go through that emulation phase. And for those who don't know, BWI is it's a Brood War API. It's an SDK they wrote that can let you write AI that plays against AI, so you can compete. There are competitions between one university writing Starcraft AI versus another AI, and so on. Very interesting AI exercises. It's in the plans to re-support BW API for Starcraft 1. If you don't know, for example, Google works with us on Starcraft 2, and they demonstrated AI for Starcraft 2 using the DeepMind AI.
How much time did you spend on this project overall?
Around 6 months. Of course, interruptions and other tasks and whatnot, but it was a long project to get it right. It's a second rewrite of it. The first one was not very robust. The second one is cleaner, and it can now live forever. It supports Mac. It can work on 64 bits. It's a proper solution.
So you said it was around 17,000 maps you found that use EUD. How many do not work with the emulator because they did dirty things or did things that were too complicated to support?
Yeah, there are in the hundreds. But I aim the telemetry that is collected by the game, we can tell how much a certain map is played. So I sort them by the most played maps, and I only target the top maps.